I just want to recap something very important here. Please remember that glucose has energy, and it has a lot of energy. Now, the reason why glucose has so much energy is because where it's coming from and the way glucose is being created in the first place. I know we haven't looked at the photosynthesis yet, and we will look at this process very soon, but I need to introduce a few elements of photosynthesis right now to explain why glucose, this very important molecule, has so much energy in it, okay? So when we think of photosynthesis, we don't need to look at all the different equations and chemistry of all of that, but what we want to know here at in this moment is that photosynthesis is a process through which carbon dioxide with water, two very simple molecules, will create glucose and, as an end product, oxygen, right? And we're happy about that because we know we breathe oxygen. That's it, okay? So what is important here is that if you look at carbon dioxide for us is a waste product, right? Whatever we're burning at this moment, all the proteins, the lipids, fats, and sugars, including glucose, every time we breathe out, carbon dioxide goes out. We breathe in, oxygen comes in, right? So basically what we're doing is this in reverse. We're using glucose plus oxygen, and we convert this into carbon dioxide and water. Now let's go back to photosynthesis. Photosynthesis does this. Plants have the ability to take carbon dioxide out of the atmosphere, convert this, and create glucose from it. Now, what you might ask at this point is like, well, isn't that carbon dioxide a small molecule that doesn't have a lot of energy and we're creating glucose? How is this possible, right? It doesn't look like an obvious reaction to me, and never did before I learned about this, right? So we know that this is a non-spontaneous reaction, so of course it will need the involvement of many different enzymes. Now, what kind of energy do we need if we want to create something from scratch that has a low level of energy, such as carbon dioxide, and we want to create glucose that has a high level of energy? Well, we need some kind of energy infusion at some point. Where do we take this? Well, this is where, this wonderful star of ours, the sun, comes into play, right? The sun, the photons of that sun will hit specialized structures inside some plants. And these plants will, the machinery will be activated. And what's going to happen is that water will be split. And from there, H2O, well, the oxygen comes from water right here, okay? And the electrons that connect the hydrogen to oxygen here, these electrons right here, will come in here and will be able to create this wonderful molecule of glucose, right? So remember, what we see here, we have a C1 molecule, carbon dioxide, but we know that glucose is a C6 molecule, right? 6 carbons. So we need a lot of electrons to do this. So now, coming back to my first question, why does glucose have so much energy? Well, glucose has lots of energy because it took energy from the sun, used electrons from water to create this C6 molecule from a C1 molecule. That's why. Now, the electrons that connect all the carbons inside that glucose molecule, That's why they have a lot of energy. Now, your metabolism right now and mine, we are kept alive because of our star. Indirectly. Because the electrons that are coming, that are included in glucose that have a lot of energy, come from come from water. And these electrons can connect the carbon dioxide, the carbons, to create glucose. So that is why glucose has a lot of energy in it. And now, please remember that, because as we move on into metabolism, and we look at cellular respiration and oxidative phosphorylation, always remember that we will be shuttling electrons throughout these processes. We'll be harvesting those electrons, and those electrons will help create ATP in the end. That's the goal. The goal is to produce energy, and the energy we use is ATP. So all of those electrons throughout the process will be harvested in order to inject that energy into the creation of ATP. Okay, so that is where this is why I want you to really understand that at this point. So throughout the process of glycolysis, and even after that, and in lots of different biochemical processes, we will be introduced, and we will see that this term here, phosphorylation, comes over and over and over again. Now, I want to make sure that you understand why phosphorylation is important and actually what phosphorylation is. So phosphorylation, what it means is that when we have a molecule and we add a phosphate group to it, that's what phosphorylation is. Okay? So it's basically adding a group to a part of a molecule. So glucose, for example, in glycolysis will be phosphorylated. Okay? Now, the question is, how does that phosphate come to be? How is it added to this molecule of glucose? So this is what we're going to look at right now, but I also want to make sure that we understand the why of phosphorylation. It seems like an extra step that's not needed, right? Well, it is needed, and let's explain that. Now, remember that when we looked at enzyme reactions, we looked at those graphs that where you have the energy of activation, or activation energy, right? So we have a component that starts at a certain level. So that's our starting molecule here, and we want to convert this molecule into something that has more energy. So at the end, the energy level, if this is the axis for the energy, at the end, the energy level will be here, which is basically higher than what we have here. In order to do this, we need to inject energy in the system. Enzymes can do this, right? We know that enzymes can make reactions that could be impossible at room temperature, or even at 37 degrees, like our 37 degrees Celsius. Enzymes make these reactions possible. But remember, in order to go to that level here, we need to go through a little bump here of higher energy right here. So basically, we need to jump a little bit in order to go down on the other side. So just think, for example, of pushing a rock, right? Pushing a rock up a hill. Well, you need, in order to have this rock stay at a certain point, you need to have a little bump so that the rock stays against that bump. So I'm not sure it's the right superb analogy here, but I just want to give you some kind of an image, right? So what we need here is to overcome this higher level of energy so that we can come down at a certain point to a stable molecule here. Remember that molecule here has more energy in it, so it's not as stable, right? So we need to remember that. Now I'm going to erase this here, and I want to bring you back to this equation, super simplistic equation, to explain something here. So just for example, think of A plus B will be converted into C. And of course, we are talking here about biochemical reactions, so usually they take enzymes, and let's call this enzyme number 1. Okay? So with the help of enzyme number 1, A and B can be combined together and form molecule C, all right? So that's just, you know, a possibility. It could be anything here, okay? So for example, think of carbon dioxide, water, and then we create C, which is glucose, as we've seen before. Now, this reaction here, even with some enzymes, it is possible that this reaction we need a little step. We need a little push towards in this direction, right? So it is possible that the enzyme is there, could do its job, but it needs a little bit of an extra push to be able to overcome that bump of activation energy. So how do we get this energy, right? How do we get it? Well, we get it from ATP. Now, how do we get this molecule from ATP? So basically what it means is that here at some point we will need to have some kind of ATP. And if we look at the reaction with ATP, so let's say something like this, then we would have our enzyme here, and then we would have the ATP reaction and then conversion into ADP, and of course a phosphate is being released, and that phosphate allows this molecule to be transformed, C to be created. It's not that simple. Okay, it looks like easy, yeah, ATP right there and everything. Doesn't make you understand why is ATP important. So let's look at that. So that's my goal here, is to explain phosphorylation, right? So I'm going to erase this here, and then what I want to do now is to explain step by step what could happen. And I say could happen because it does not always happen in this sequence. But I just want to give you something generic that you can fall back on to understand the more complex equations or processes after that. So let's simplify. Let's keep things simple. So we have this here, like my equation here again. So A plus B leads to C with the help of enzyme number 1. But we know that this reaction is not possible. We cannot do this. We need an extra push of energy. And we know that ATP can be used, right? So ATP here, ATP to ATP. Now what I want to show is how this ATP is actually being used. There you go. So let's look at that. What we have here is that we would have, for example, we would have a reaction that would go like this. We would have A, and A would be converted into a phosphorylation state. So what we do is we add this phosphate to it. And where is this phosphate coming from? Well, we had triphosphate here. We had 3 phosphates, and then we're done with 2 when after this reaction happens. So this extra phosphate is now added to A. So you see that just the fact that we added a phosphate to A here, this A, phosphorylated A, has now a higher level of energy than A. So the enzyme now has something to work with that it can try. We're on a good pathway to the creation of C right here. So we created this part here. A is activated. And now A being activated by having an extra phosphate can now react to B, with B, and create C. Okay? It is possible that B would need to be phosphorylated as well. I want to keep simple, I won't do that, but just keep that in mind. Now, when we create C, when C is being synthesized, we say, C will still have the phosphate on it unless it's been removed. But I want to go step by step, so I will now add the phosphate to it, which is the same phosphate that was on A, right? Remember that A and B reacted, formed this new molecule that formed C, but the phosphate was never removed, so we still have it. And then if our goal is to create C without a phosphate, then we will need to remove that phosphate right there. Okay? So, here's what happens. When we look at this equation here, right? what we have is this, and I already explained that. And the phosphate, we know that this phosphate comes from ATP, and then we have ADP, right? And then at the end, we remove the ADP, we remove the phosphate here. So what's going to happen is that this ADP here could be converted back into ATP, okay? So you see that here we added a phosphate, and in this case we remove the phosphate. We know that there is an enzyme here that is needed for this reaction. We call it enzyme number 1, okay? There are 2 more enzymes that are needed here. It takes an enzyme to add a phosphate to a molecule. It just doesn't happen just like that, right? It's not a spontaneous reaction. So we need an enzyme for that. So we will say that this enzyme here, let's call it enzyme A, right? Because it adds a phosphate to A. And then here, it removes the phosphate from C, so let's call that enzyme C. Hopefully you're following, okay? Right here. So this enzyme has an action right here, the enzyme has an action right here. Now, the goal, the job of the enzyme A is to add a phosphate to A. These enzymes have a special name, okay? The enzyme that adds a phosphate, okay? So if you add a phosphate, if you add a phosphate, the name of the enzyme for this is a kinase. Okay? When you add a phosphate, kinase. So enzyme A is a kinase. When you remove, if you remove the phosphate, then you have another type of enzyme. These enzymes have a name, and they're called phosphatase. So enzyme C is a phosphatase. Okay? Kinase, adding a phosphate, phosphatase, removing the phosphate. Okay? So you see that A plus B gives C is a little bit more complex than it was. Now, keep that in mind, because what I want to do now is go into glycolysis and look at the steps and explain what we have here. Remember, the goal at the end of the whole process of respiration is to create energy that we can use, that keeps us alive, right? So we want to create ATP. We don't want to consume it all the time. We want to create more than what we need, right? So that's the goal of respiration, and that's where we're going now. We will look here at a very simplified glycolytic pathway. So basically is what happens to glucose when we start extracting electrons from it and preparing that molecule so that more electrons can be extracted down the road through oxidative phosphorylation, which we haven't seen yet. Okay, so stay tuned for that. So before I start, I just want to show that I have some symbols here. So just so you know that when there's a G, it means that's glucose. If we have an F, that's fructose. If we have a P, pyruvate, I wrote pyruvate here, and if we have ACoA, acetyl coenzyme A, as we have here. Okay, so that's the kind of like the legend. So please refer back as you watch this video. Look at this. Okay, so the first step here is that your cells and the glycolytic pathway happens inside the cell, in the cytoplasm. Okay, in the cytoplasm. So glucose will be shuttled inside the cell so that the cell can create energy from that. And glucose will be prepared for the enzymes to be able to have some kind of an action on it to extract the energy. So what happens here is that we see that we have glucose 6-phosphate. So what does that mean, 6-phosphate? Does it mean there's 6 phosphates? No. It means that there is a phosphate on carbon number 6 of glucose, right? That's what it means, okay? In order to have phosphate here, where do we take the phosphate? Well, you guessed it, we take this from ATP. So we have ATP conversion into ADP, right? And the action of this enzyme here that adds the phosphate to the glucose is a kinase, right? Remember the enzyme that adds phosphate to molecules? Their names are kinase. What would we have here? The enzyme that's responsible for this action is called hexokinase. Hexo meaning 6. Why 6? Because it has 6 carbons. Okay. So hexokinase is the enzyme that's going to add a phosphate to this glucose, and it will on position 6, so it will become glucose 6-phosphate. Now, the next step after that, and there are 10 steps when you look at glycolysis, right? So I did not write all those steps here, but the next step here is to convert glucose into fructose. Okay, so what we have here is an enzyme that's here, and this enzyme is going to convert glucose to fructose. Basically what it is just a rearrangement of the molecule. So it changes a bond here and there, and that creates fructose. Fructose is quite similar to glucose, but if you look at the structure, you'll see the difference between them. So remember that we never remove the phosphate. So we have glucose 6-phosphate. If we rearrange this molecule into fructose, then we have fructose 6-phosphate. The phosphate is still there. Now, if we look at the next step after that, is we have fructose that has a phosphate at position 1 and 6. That's why we have BP here for biphosphate or diphosphate. You could have like DP, depending on the textbook or whatever you look, but one or the other. Biphosphate, diphosphate, doesn't matter. We know there's two phosphates. Why? Where are they? Phosphates are now in position 1 and 6. Carbon number 1, carbon number 6. So we already had a phosphate here. We're adding a new one. Where does that phosphate come from? Well, of course, it comes from the same spot. It comes from another molecule of ATP that will be converted into ADP. And you guessed it, the enzyme, a kind of enzyme that is responsible for this is a kinase. Then we move on several steps here, which I didn't detail here. And then we move on from a carbon 6 molecule, so 6 carbons, we'll move on to pyruvate that has a 3-carbon molecule. So from 6 to 3, you might think, where are the 3 other carbons? Well, they're just there. We just have 2 times 2 molecules of pyruvate that will be created, right? So it becomes a C3 molecule. And then what happened here is that you see pyruvate here does not have phosphate. It doesn't have phosphate on it. So what do we need? Well, we'll need phosphatase, right? We'll need enzymes that will remove these phosphates. So in order to remove this, we will have ADP, and we'll create ATP from it. Okay? So that when this happens, when we create ATP, based on the action of a phosphatase that removes a phosphate from somewhere and adds it to ADP, there's a name for that, okay? And that name for this, it's called substrate level phosphorylation. I don't have enough space, but phosphorylation, like we've seen before, okay? So ATP here is created from phosphate level phosphorylation. From substrate level phosphorylation. So there's only a few molecules of ATP that are created this way. This is not the major way where our cells create ATP, but there's a little bit of it here. And then there's more enzymes that will be used here, will get into action. And then we will create the acetyl coenzyme A, which is a 2-carbon molecule. Okay? And then from there, we will go into the Krebs cycle, the citric acid cycle, and that's the next step. Okay? So what I wanted to show here is just to apply what we've seen before, is that there are conversions of different molecules here in using ATP just to boost the energy level up, but this ATP is added with kinases, and there's another enzyme after that that will extract the phosphates from the molecules and will create ATP from there.